Welcome back to the AI podcast. I'm Alex, and today we are tackling something that quite literally every company building with AI right now is dealing with. RAG, retrieval-augmented generation. It's become the default architecture for building AI products on top of enterprise data. And my guest today is going to tell us why most implementations are fundamentally broken. Sofia Petrov is the head of AI at Brex, previously a principal engineer at Notion, where she helped ship Notion AI. And before that, she was at Google Research, working on retrieval and ranking for Google Search. Sofia, welcome.
Thanks, Alex. Really excited to be here. RAG is one of those topics where I have a lot of opinions and I'm not shy about sharing them.
And that's exactly what we need, because your blog post, Your RAG is Broken and You Don't Know It, had over 200,000 readers and started a massive conversation in the engineering community. What made you write it?
Frustration, honestly. I kept seeing the same patterns over and over. Companies would follow a RAG tutorial, get a prototype working that looked pretty good on a handful of test questions, and then deploy it to production. And within weeks, users would start complaining that the system was making things up, giving wrong answers, or completely ignoring relevant information that was right there in the knowledge base. And the teams building these systems had no idea why because their evaluation metrics said everything was fine.
Fun. Feel a snarvium. Mother fun. Read the press cert of an emotional story. Though do not care. So, one of you, Thimir, could mean to Gerlays because you're here.
A massive gap. And this is the core problem with RAG today. The standard approach to building a RAG system is conceptually simple. You take your documents, you split them into chunks, you embed those chunks into vectors, you store them in a vector database, and at query time, you retrieve the most relevant chunks and give them to the LLM as context. And conceptually, that's correct. But every single step in that pipeline has failure mode that most teams don't understand. And those failures compound in ways that produce a system that looks like it works until you actually scrutinize the outputs.
That reminds me of the AI technical debt conversation we had a few episodes ago. Silent failures that don't crash the system but degrade the quality.
Exactly the same dynamic. Your RAG pipeline never throws an error, it always returns an answer. The question is whether that answer is actually grounded in your data or whether the model is hallucinating something plausible sounding. And distinguishing between those two cases is shockingly hard without proper evaluation infrastructure.
So, where do most teams go wrong first?
Retrieval. And this might sound obvious, but I cannot overstate how much the industry has underinvested in retrieval quality. Everyone is obsessed with which LLM to use, which generation model gives the best answers. And yes, model quality matters, but if you're feeding the model irrelevant or incomplete context, it doesn't matter if you're using GPT-4 or Claude or Gemini. Garbage in, garbage out. The retrieval step determines the ceiling of your RAG system's quality, and most teams treat it as a solved problem because vector databases are easy to set up.
Let's dig into retrieval then. When you say most teams treat retrieval as solved, what are they missing?
They're missing the fundamental gap between semantic similarity and semantic relevance. These are not the same thing, and conflating them is the root cause of most RAG failures. Let me explain. When you embed a query and retrieve the top k chunks by cosine similarity, you're finding chunks that are semantically similar to the query in the embedding space. But similarity and relevance are different concepts. Two texts can be similar without being relevant to answering the question.
Can you give me an example of that?
Sure. Imagine your knowledge base contains a company's HR policy documents. A user asks, "What is the parental leave policy for employees in California?" Your embedding model will find chunks that are semantically similar to that question. It might retrieve a chunk about parental leave in New York, a chunk about general California employment law, and a chunk about the employee benefits overview. All of these are semantically close to the query, but none of them specifically answer the question about parental leave in California. The actual relevant chunk, the one that says employees in California get 16 weeks of parental leave, might be ranked 6th or 7th because its embedding is slightly farther from the query in vector space.
So the right answer is in the knowledge base, but the retrieval step fails to surface it at the top of the results.
Exactly. And when the LLM receives those top 5 chunks that are related but not directly relevant, it does one of two things. Either it says, I don't have enough information to answer, which frustrates the user, or worse, it synthesizes an answer from the partially relevant chunks. It might say, based on the company benefits overview, parental leave is 12 weeks because that's the default mentioned in the general policy, even though California employees actually get 16 weeks. The answer sounds confident and is almost correct, which makes it incredibly dangerous.
That's terrifying from a compliance standpoint. An employee could make decisions based on wrong information because the AI confidently told them the wrong number.
Exactly. And this is why I say retrieval is the hard part, not generation. The generation model is doing exactly what you asked it to do, answer based on the provided context. The problem is that the provided context is wrong or incomplete.
So, what's the solution? Better embedding models?
Better embedding models help, but they're not sufficient. The real solution is a layered retrieval architecture. At Notion, when we built Notion AI, we learned very quickly that pure vector search was not enough for production quality RAG. We ended up building a 3-layer retrieval system. The first layer is traditional keyword search using BM25. This catches the exact match cases that embedding models sometimes miss. If someone searches for a specific policy number or a technical term, BM25 finds it reliably. The second layer is vector search using a fine-tuned embedding model. This handles the semantic understanding. And the third layer is a re-ranker, a cross-encoder model that takes the combined results from layers 1 and 2 and rescores them with a much more nuanced understanding of relevance.
So, you're combining the precision of keyword search with the flexibility of semantic search, and then using a more powerful model to sort the results.
Exactly, hybrid search with re-ranking. And the re-ranking step is where the magic happens. Cross-encoder re-rankers are much more accurate than bi-encoder embedding models because they see the query and the document together as a pair rather than encoding them independently. The accuracy improvement from adding a re-ranker is typically 15 to 25% on retrieval precision. That's massive.
15 to 25% improvement just from re ranking. That seems like a no brainer.
It is absolutely a no-brainer, and yet the majority of RAG implementations I review don't use one. They rely entirely on single-stage vector search. It's like building a search engine in 2025 that only uses PageRank without any query understanding. Google solved this problem 20 years ago with multiple retrieval stages. The RAG community is relearning these lessons from scratch.
All right, let's talk about chunking. You mentioned in your blog post that chunking is where most RAG systems quietly destroy themselves. What do you mean by that?
Chunking is the process of splitting your documents into smaller pieces that can be embedded and retrieved independently. And the way you chunk your documents has an enormous impact on retrieval quality. But most teams think about chunking for about 5 minutes. They set a chunk size of 500 tokens with a 100 token overlap and move on. That default configuration works terribly for most real world documents
Why does it work terribly?
because documents have structure, and fixed size chunking ignores that structure completely. Think about a legal contract. It has sections, subsections, clauses, definitions that reference each other. If you chunk it into 500 token pieces, you're going to split clauses in the middle, separate definitions from the terms they define, and create chunks that are incoherent on their own. When a user asks, what are the termination conditions in this contract? The retrieval system might find a chunk that starts in the middle of a termination clause and ends in the middle of the next section. The LLM gets this fragment and has to guess what it means in context.
So, fixed size chunking destroys the semantic coherence of the source material.
Exactly. And the problem gets worse with certain types of documents. Tables are a nightmare. If you have a financial report with tables of numbers, fixed size chunking will split tables across chunks, separating column headers from their values. The LLM receives a chunk that has numbers but no context for what those numbers mean. I've seen RAG systems confidently report that revenue was $47 million when the actual number in the table was the accounts receivable figure. The revenue was in a different chunk that didn't get retrieved.
So, how should teams approach chunking instead?
There are several strategies that work much better depending on your document types. The first is semantic chunking. Instead of splitting on token count, you split on semantic boundaries. Paragraph breaks, section headings, topic shifts. There are good libraries that detect topic changes in text and split accordingly. This preserves the natural structure of the document.
Now, that sounds computationally more expensive, but much higher quality.
It is, and it's worth it. The second strategy is hierarchical chunking. You create chunks at multiple levels of granularity. You have the full document summary, section level chunks, and paragraph level chunks. At retrieval time, you can start with the section level to get the right neighborhood and then drill down to the paragraph level for specifics. This mimics how a human would actually search through a document. You'd scan section headings first, then read the relevant paragraphs.
What about that table problem you mentioned?
Tables need special handling. What we do at Brex is we extract tables as structured data and create dedicated table chunks that include the full column headers, row labels, and values together as a single unit. We also generate a natural language description of each table, something like this table shows quarterly revenue by product line for fiscal year 2024, and we embed that description alongside the structured data. That way, the table gets retrieved when it's semantically relevant, and the LLM has the complete table to work with.
That's really clever. You're creating a dual representation, one for retrieval and one for the LLM to reason about.
That dual representation pattern is really powerful. We use it for images too. We generate captions for diagrams and charts and embed the captions for retrieval while passing the original image to a multimodal LLM for generation. The retrieval index and the generation context don't have to be the same thing, and teams that realize this build much better systems.
I feel like that's a profound insight. The thing you search on doesn't have to be the thing you read.
Right. And this applies in so many ways. You can embed a question that a chunk answers rather than the chunk itself. We call these hypothetical document embeddings or sometimes question index chunks. Instead of asking, is this chunk similar to the query? You're asking, does this chunk answer a question that's similar to the query? And that reframing dramatically improves retrieval quality for question answering use cases.
So we've talked about retrieval quality and chunking, but how do you actually know if your RAG system is good? How do you measure it? Because you mentioned earlier that most teams' evaluation metrics are lying to them.
Evaluation is honestly the most underinvested area in the entire RAG ecosystem, and I think it's the most important. Let me tell you what most teams do for evaluation and why it's insufficient. The typical approach is to create a set of maybe 50 to 100 test questions, run them through the RAG pipeline, and eyeball the answers. Maybe they have a few engineers rate the answers on a scale of 1 to 5, they compute an average score, it looks good, and they ship it.
What's wrong with that approach?
Several things. First, 50 to 100 questions is nowhere near enough to characterize the behavior of a system that will handle thousands of diverse queries. You're sampling a tiny corner of the input distribution. Second, human evaluation is incredibly inconsistent. If you have 3 engineers rate the same answer, they'll often disagree on the score. Third, and most importantly, this approach measures answer quality, but not retrieval quality. And as we've established, retrieval quality is the bottleneck.
So you need to evaluate retrieval and generation separately.
Exactly. You need what I call the 4 pillars of RAG evaluation. The first pillar is retrieval precision. Of the chunks you retrieved, what percentage were actually relevant to the question? If you retrieve 5 chunks and only 2 are relevant, your precision is 40%. That means 60% of the context you're feeding the LLM is noise.
And noise in the context can actually hurt performance, right? More isn't always better.
Such a good point. There's overwhelming evidence that including irrelevant context degrades generation quality. The LLM gets confused or distracted by information that looks related but isn't. This is why retrieval precision matters so much.
What's the second pillar?
Retrieval recall. Of all the chunks in your knowledge base that are relevant to the question, what percentage did you actually retrieve? If there are 3 relevant chunks and you only found 1, your recall is 33%. The LLM might give a partial answer because it's missing 2/3 of the relevant information.
How do you measure recall? It seems like you need to know in advance which chunks are relevant for every query.
You do, and that's why building a proper evaluation dataset is hard work. At Brex, we have a team that manually annotates relevance judgments for our evaluation queries. For each test query, we have humans identify every chunk in the knowledge base that contains information needed to answer the question correctly. It took us about 3 weeks to build our first evaluation set of 500 annotated queries. But that investment has paid for itself many times over because we can now measure every change to our retrieval pipeline with precision.
That's a significant upfront investment. What are the third and fourth pillars?
The third pillar is faithfulness. Given the retrieved context, does the generated answer actually reflect what the context says, or does the model hallucinate information that isn't in the chunks? This is where you catch the model adding facts or numbers that aren't grounded in any retrieved document. You can measure this automatically using an LLM as a judge. You give a judge model the answer and the context and ask it to identify any claims in the answer that aren't supported by the provided context.
So you're using AI to evaluate AI.
You are, and it works surprisingly well when you set it up carefully. The fourth pillar is answer completeness. Given the relevant information that was retrieved, does the answer fully address the question? A system can be faithful but incomplete. It might correctly report one fact from the context while ignoring 3 other relevant facts. Users experience that as the system only giving partial answers.
So a comprehensive RAG evaluation measures retrieval precision, retrieval recall, faithfulness, and completeness. That's much more rigorous than what most teams are doing.
It is. And once you have these 4 metrics, you can diagnose problems precisely. If faithfulness is low but retrieval is good, your model is hallucinating, consider a better model or better prompting. If retrieval recall is low, your embedding model or search strategy isn't find relevant documents. If precision is low, you're retrieving too much noise, add a re-ranker. Each metric points you to a specific part of the pipeline to improve. Without them, you're debugging in the dark.
Let's talk about production architecture. You've shipped RAG at Notion scale and now at Brex. What does a production RAG system actually look like when it needs to serve millions of queries reliably?
It looks a lot more complex than the prototypes, that's for sure. Let me walk you through the architecture we built at Brex because I think it illustrates the key patterns well. The first thing to understand is that a production RAG system isn't just a retrieval pipeline, it's an entire data platform. You need an ingestion pipeline that processes new and updated documents continuously. You need an indexing layer that maintains your search indexes. You need a query pipeline that handles retrieval, re-ranking, and generation. And you need a monitoring layer that tracks quality in real time.
So there are 4 distinct systems that all need to work together.
Right. And let me start with ingestion, because this is where a lot of production systems struggle. In a prototype, you ingest your documents once and you're done. In production, documents change constantly. Policies get updated, contracts get amended, knowledge articles get revised. Your pipeline needs to detect changes, rechunk the modified documents, re-embed the new chunks, and update the index, without disrupting live traffic.
That's essentially a streaming data pipeline for unstructured data.
Exactly, and it comes with all the challenges of streaming systems. You need to handle duplicate detection because the same document might get ingested through multiple channels. You need versioning so you can roll back if a batch of documents was processed incorrectly. And you need freshness guarantees. If a policy changes, how quickly does the RAG system reflect that change? At Brex, our SLA is 15 minutes. A document update should be searchable within 15 minutes of being modified. That requires a pretty sophisticated pipeline.
15 minutes is fast. How do you achieve that?
We use a change data capture pattern. We monitor our document stores for changes and feed updates into a processing queue. Each update gets chunked, embedded, and indexed incrementally. We don't reprocess the entire corpus, only the change documents. That keeps the latency low and the compute cost manageable.
What about the query pipeline itself? Walk me through what happens when a user submits a question.
Sure. When a query comes in, the first thing we do is query understanding. We reformulate the user's question to make it more retrieval friendly. Users ask messy questions. Things like, what was that thing about the Q3 numbers? We use a lightweight LLM to expand that into a clearer query while preserving the user's intent. Then we run parallel retrieval. We fire off both a BM25 keyword search and a vector search simultaneously. We merge the results using reciprocal rank fusion, which combines the rankings from both systems in a principled way.
Yep.
Then we run the re-ranker to rescore the merged results. We take the top chunks from the re-ranker and do a final step we call context assembly.
What's context assembly?
Context assembly is where we construct the actual context window that gets sent to the LLM. This is more nuanced than just concatenating the top 5 chunks. We do a few things. First, we add surrounding context. If a retrieved chunk is paragraph 3 of a section, we include paragraphs 2 and 4 as well to give the LLM more context. Second, we deduplicate. Sometimes multiple chunks contain overlapping information, and including both wastes context window space. Third, we order the chunks. We experimented extensively and found that putting the most relevant chunks first and last, with less relevant ones in the middle, produces better answers. This is consistent with research of the lost in the middle problem.
The lost in the middle problem?
There's research showing that LLMs pay more attention to information at the beginning and end of their context window and tend to miss information in the middle. So we exploit that by strategic positioning. The chunk most likely to contain the answer goes first. The second most likely goes last. Everything else goes in the middle.
That level of attention to the generation step is something I hadn't even considered.
And that's the point. Every step in the pipeline can be optimized, and the compounding effect of optimizing every step is dramatic. We measured it. Going from our V1 naive RAG implementation to our current production system improved end-to-end answer quality by over 40% on our evaluation benchmarks. And about half of that improvement came from retrieval changes, and the other half from these kinds of generation optimizations.
All right, Sophia, let's look forward. RAG has been the dominant paradigm for about 2 years now. Is it going to stay that way, or is something better coming?
I think RAG as a concept is here to stay, but the implementation patterns are going to change dramatically. What we call RAG today, the simple retrieve and generate pipeline, is going to look as primitive as early web search looks compared to Google search today. Let me explain what I mean.
Please.
There are 3 major shifts I see happening. The first is the move from passive retrieval to active retrieval. Right now, RAG is a one-shot process. You get a query, you retrieve once, you generate. But humans don't research that way. When you're trying to answer a complex question, you search, read some results, realize you need to refine your search again with better terms, cross-reference multiple sources, and gradually build up an understanding. The next generation of RAG systems will do the same thing. The model will retrieve, read, decide what's missing, formulate a follow-up query, retrieve again, and iterate until it has sufficient information.
So the model becomes an active participant in the retrieval process rather than a passive consumer.
Exactly, and we're already seeing early versions of this with agentic RAG patterns. The model has access to a search tool and can call it multiple times with different queries during a single generation. At Brex, we've been experimenting with this, and the improvement on complex multi-fact questions is significant. Our accuracy on questions that require synthesizing information from multiple documents went from 68% to 84%.
That's a huge jump. What's the second shift?
The second is the integration of structured and unstructured data in a single retrieval framework. Right now, most RAG systems only handle unstructured text, documents, articles, knowledge bases, but in enterprise environments, a huge amount of critical information lives in structured systems. Databases, spreadsheets, CRM record, analytics dashboards. A user asking, how did our enterprise revenue compare to forecast last quarter? Can't be answered from documents alone. You need to query a database, retrieve the relevant data, and potentially combine it with context from a quarterly review document. The future of RAG is multimodal in the data sense, seamlessly combining text retrieval with SQL generation, API calls, and structured data lookups.
That sounds like it converges with the AI agent space.
It does, and I think that convergence is inevitable. RAG becomes one capability within a broader agent framework. The agent decides whether to search documents, query a database, call an API, or in some combination of all 3. The retrieval step becomes a tool that the agent uses, not the entire architecture.
And the third shift?
The third is personalized retrieval. Right now, RAG treats every user the same. The same query gets the same retrieved context regardless of who's asking. But in practice, the relevant information depends heavily on the user's role, permissions, history, and context. When a finance team member asks about the Q3 numbers, they want the detailed P&L breakdown. When a sales rep asks the same question, they want the revenue highlights they can share with prospects. Personalized retrieval means the system understands who's asking and retrieves accordingly. At Brex, we've started implementing this with role-based retrieval profiles that adjust the search weights and filters based on the user's department and seniority level.
That's a really elegant approach. Before we wrap up, what's your one piece of advice for someone who's building a RAG system right now?
Invest in evaluation before you invest in anything else. Build your evaluation dataset first. Annotate the ground truth relevance judgments. Set up the 4-pillar metrics I described. Once you have that foundation, every change you make to your pipeline can be measured and validated. Without it, you're flying blind. I have watched teams spend months optimizing their chunking strategy and embedding model only to discover through proper evaluation that they made things worse. Measurement first, optimizing their chunking strategy.
Measurement first, optimization second. That's the kind of discipline that separates production systems from prototypes. Sofia Petrov, head of AI at Brex, thank you so much for joining us on the AI podcast.
Thanks, Alex. It was a blast.
And to our listeners, if you're building with RAG, and let's be honest, most of you are, take Sofia's advice to heart. Measure your retrieval quality before you ship. The answers your system gives are only as good as the context it retrieves. We'll see you next week on the AI podcast.